네, 오늘은 스태틱 포트폴리오 초이스에 대해서 볼 겁니다. 즉, 에이전트들이 어떠한 포트폴리오 셀렉션을 옵티멀하게 하는지 볼 거고요. 두 가지 스페셜 케이스를 볼 거예요. 첫 번째는 CARA-Normal 케이스. 유틸리티 펑션이 constant absolute risk aversion으로 주어지고, 즉 exponential 펑션이죠. 이렇게 주어지고 asset return은 normal return을 띌 때, 이 경우에 closed form 솔루션으로 옵티멀 포트폴리오 셀렉션이 나오게 됩니다. 두 번째 경우는 이제 CRRA and log normal case. 그러니까 constant relative risk aversion, risk aversion coefficient가 relatively constant일 때, 그리고 이제 return distribution이 log normal을 띌 때, 이 경우에도 closed form solution이 나오게 돼요. 그래서 이 두 경우에 포트폴리오 셀렉션이 어떻게 되는지 보고, 특히나 이 두 경우 되게 비슷하게 나옵니다. 즉, excess return과 variance만의 펑션으로 나오는데, 그게 어떻게 데리베이션 되는지 보고 그에 따른 경제학적인 분석을 할 거예요. So in this class, we will take a look at static portfolio choice. We will focus on two special cases. The first one is CARA-Normal return case. So the utility function is constant absolute risk aversion, and the asset return is given as normal distribution. And the second case is CRRA, constant relative risk aversion utility function with log normal case. So today's lecture is mostly based on Campbell chapter 2. So you can read it, and for any questions, you can take a look at the text, and also you can bring them to me. So in terms of the setting, it's going to be similar to the previous case. 그래서 지난 시간에 봤듯이 간단한 consumption based asset pricing case와 똑같은 세팅을 쓸 겁니다. So we are going to use the same setting as before. So that the payoff of an asset is xt plus 1. So that's the payoff in the next class, next period. And the stock return is current future stock return price plus the dividends. And the dividend is paid at t plus 1. 그리고 risk-free bond를 가정할 거고요. There's a risk-free bond whose face value is f. And the one period's gross return is denoted as rt plus 1. Where the return is future payoff divided by the current price, and so on. And we will assume there's a risk-free rate, which is RF. Another thing I want to mention here is that, so whenever I use the lower capital letters, for example, RT plus 1, this is basically log return. Okay? So similarly, I will also use lower capital letter for the RF as well. That's the log return for the risk-free rate. So that's the basic notation, basically the same as the previous lectures. There are some cases of utility functions that are very tractable. The first one is the quadratic utility. Why is that called the quadratic utility? Because utility is the function of the quadratic function of the future wealth. Okay? So quadratic utility, of course, is very easy to handle because if you just take the derivative, then you get a linear function. But there's downside because, as you can see, the utility function has a saturation point. Okay? So after a certain saturation point, here it should be negative eta. So once the wealth is actually 2 times eta. Once the wealth goes above this value, then utility becomes a decreasing function, which is not very good. So in any case, if you use quadratic utility function, then you can also get optimal portfolio choice very easily. But more popular cases are the following two cases. The first one is the exponential utility, or the CARA utility function, a constant absolute risk aversion case. In this case, the utility is given as like this. Okay? 즉, utility function이 exponential하게 주어질 때, exponential utility로 주어질 때, 또 portfolio selection을 또 쉽게 구할 수가 있어요. 이 경우에는 utility function이 이렇게 주어지겠죠? 잠시만요. 다시 그립시다. Okay, so this is wealth and this is utility. Okay? So it is bounded above. Okay, bounded above. That's the property of the CARA utility function, or the constant absolute risk aversion utility function, where alpha here is the risk aversion coefficient. Okay. Another class of utility function that is very popular and easy to deal with is constant relative risk aversion case. Constant relative risk aversion case. Here, the utility function is given in this fashion, as you see here. Okay. And when gamma is 1, so 여기서 gamma가 1으로 가면 이 utility function은 log utility function인데요. In other words, you can actually calculate it. When gamma approaches 1, then using the L'Hopital rule. L'Hopital 룰을 사용하면 이제 위아래를 미분을 해주면 이거의 이 펑션의 이제 극한값을 구할 수 있게 되죠. I'm sorry about that. It's not 1. I'm sorry. It should be log of W. Okay. So when gamma is 1, it's the special case and it becomes a log utility. But when gamma is not 1, in other words, when gamma is greater than 1 or gamma is less than 1, and then it's just the usual CARA utility function. I'm sorry, the constant relative risk aversion case. And in this lecture, we will only consider the case where gamma is less than 1. Okay, so that's the basics. That's the background of the utility functions that we're going to use. And then we will actually move on to the portfolio trace case. Okay, so again, as I said, we will consider the CARA-Normal case. So the utility function is the negative of the exponential function, and the asset returns follow normal distribution. 그래서 여기서는 CARA, Constant Absolute Risk Aversion Utility Function을 쓸 것이고요. Asset return은 normal distribution을 따른다고 가정을 할 겁니다. 그리고 이제 인베스터들 원 피리어드만 있고요. 자, initial wealth가 W예요. 즉 W라는 돈을 가지고 있고, that's the initial wealth, and the investor is going to decide. The W portion. W만큼의 돈이 있는데 이 중에서 theta 달러는 risky asset 넣고요. 세라만큼 어마운트는 risky asset에 넣고 1 minus theta는 risk free asset에 들어갈 겁니다. Okay. Now, what is the distribution of this risky asset? Risky asset is following the distribution like that. So the risky asset is going to generate R T plus 1. Let's just say R. Okay, so R is the return on the risky asset, and that is assumed to be RF plus X. Okay? So X is the random portion. RF is known because RF is the risk-free asset. 즉 RF는 risk-free asset이고 X가 random variable이에요. 즉 X는 이걸 그냥 rearrange를 하면 excess return이라고 볼 수 있죠. X is the excess return on the risky asset. 그리고 X가 normal distribution을 따른다고 가정할 거예요. And X follows the normal distribution with mean M and the standard deviation of sigma. And as I said, we assume that the utility function is CARA or exponential with the risk aversion coefficient of A. In that case, utility function is given as U of C equals negative of exponential of negative A times C. Now, investors' wealth in the next period is given in the following way, because he or she is investing theta dollars in the risky asset. 즉 theta만큼을 risky asset에 넣고 나머지 W 마이너스 theta를 risk free asset에 넣잖아요. 그러면 어떻게 됐어요? 즉 theta를 risk에 넣고 그러면 theta가 있었는데 이 theta가 next period에 theta times x가 되겠죠? 예? 그리고 W minus theta is in the risk-free asset, and that's going to become risk-free asset에 넣었으니까 이만큼을 벌어들이겠죠. So your wealth, the investor's wealth in the next period becomes 이 두 개 더해야죠. You have to sum them up. So it's theta x plus W minus theta times RF. 즉 이게 인베스터의 next period wealth가 됩니다. 자, 이거를 이걸 다시 리어레인징을 하면요. 자, 이것을 리어레인징을 하면 잠시만요. There was an error. There was an error here. 즉 theta가 risky asset에 있었는데 risky asset의 return은 이렇게 되죠. RF plus X. Okay? Because that was the return on the risky asset, right? So if I rewrite it, 어떻게 되죠? 그러면 이 두 개를 더해야죠. 이 두 어마운트를 더하면 그것이 So this is the return coming from the risky asset. I'm sorry, the payoff. And this part is coming from the risk-free asset. Okay? And if you rearrange it, and then you calculate this, and you come theta times x plus w times rf. Okay? 그럼 따라서 어떻게 되냐면 이제 wealth는 next period wealth becomes w times rf plus theta times x. Okay, so basically it's the same expression as here. Okay, basically. Okay. And there's actually a typo. Meaning there should be no 1 plus alpha here. Okay, 1 plus. Okay. Now then the investor optimization problem then becomes the following. So the investor's optimization problem is simply the optimizing the expected utility based on the wealth in the next period. Okay, and because we know the utility function, what is the utility function here? The utility function is this one, because the utility function is that one, okay? And because there was a negative sign here, therefore this maximization problem becomes a minimization problem, okay? And then it's the same thing. Okay, and now it is the same as minimizing. Okay, so let me. Okay, so now that's the investor optimization problem. So minimizing over theta of the expected value of E to the negative W0 plus theta X. Okay. And we know that X follows a normal variable with mean M and sigma squared, right? And then what is the key here? We know very important property of the log normal random variable, meaning, so suppose there's a, suppose there's a normal variable with, okay, I'll just write it in this fashion, okay? Now, then it's the same as, we will come back to here. We will come back to this, okay? But let me just rearrange it a little bit. So it becomes minus A times W0 minus A times theta times X, okay? Now, this can be rewritten as E to the minus A W0 E to the minus A theta X, okay? And we know that minus A theta X then follows a normal random variable of, what is the mean? Mean, you just multiply this to the M, and the variance, it will be squared. Okay. 자, 이렇게 되겠죠? 네? 이렇게 됩니다. 자, 그러면 we can calculate this. E, the average is A theta M plus a half times A squared theta squared theta squared. Okay. That's the very important property of the log normal random variable. Okay. So basically it is the same as minimizing minus A W0 minus A theta M plus a half of A squared theta squared sigma squared over theta. 그럼 이거 미니마이즈 하는 거랑 똑같죠? Why? 왜냐면 이게 exponential function이 있어 increasing function이니까 그냥 여기에 있는 그 펑션 내에 있는 베리어블에 대해서 미니마이즈 시켜주면 똑같아요. 그럼 어떻게 하죠? We take the derivative with respect to theta. theta에 대해서 derivative를 취해주면 편미분을 하면요. a theta plus a squared 이렇게 되죠. 그리고 이게 0이 돼야 되죠. 이게 0. Something's wrong. 이렇게 돼야 되죠. 그럼 theta는 어떻게 돼요? theta는 m over a sigma square 이렇게 됩니다. 자, m이 뭐죠? m이 payoff의 평균 average of x and sigma square is the variance of x 이렇게 됩니다. 그래서 그 결과가 이거예요. Well, the first thing you need to know is again it is basically the one here that is here is basically the same trick that I used. In other words, it follows from the very important property of log normal random variable that we learned many times. We have repeated over and over, where mu and sigma are the average and standard deviation of excess return x on the risky asset. 이 앞에 슬라이드에서는 I used m instead of mu, but they should be the same thing. Whether it's m or mu, they are the same things. Okay. So they are the same things. We have done this many times before. Now, the first of the condition that we derived in the previous slide, which is the theta. Theta is basically this expression here. Okay. Now, what is important here is that because of the property of the utility function is constant absolute risk aversion function, right? So regardless of your level of wealth, the risk aversion is constant. So your portfolio choice, the dollar amount the investors put in the risky asset is not a function of wealth, which is W. 자, 여기서 중요한 프로퍼티가 하나 나오는데요. 자, 여기서 first under condition이 말하는 세타를 봅시다. 세타, 여기 있죠? 이 세타가 뭐였죠? 세타는 dollar amount in the risky asset. 내가 얼마만큼이냐 리스키 에셋에 투자를 할 건데 저 어마운트에 current wealth가 들어가지 않아요. 무슨 말이죠? 자, 내가 가난하건 부자이건 간에 주식시장에 들어가는 양은 일정하다는 뜻이에요. 내가 가난해도 주식시장에 100만 원어치 투자를 하고 내가 빌 게이츠만큼 부자라고 해도 주식시장에 100만 원밖에 안 들어가는 거예요. That's a very important unrealistic characteristic of the CARA utility function. 별로 현실적이진 않죠. 자, 여기서 또 어떤 점을 우리가 볼 수 있습니까? What other property that we can observe from this, the first order condition? The optimal amount you want to get into the risky asset is increasing in mu. 즉, excess return이 높으면 when mu is high, excess return이 높으면 risky asset을 더 많이 사게 돼요. demand가 증가한다는 것입니다. And when sigma is high, theta is low. It's a very intuitive result. What is theta? theta는 리스키 에셋에 대한 디맨드예요. 내가 리스키 에셋을 얼마나 살 건지에 대한 디맨드입니다. 이 디맨드는 크게 봐서 두 가지의 지금 좌우가 돼요. 첫 번째, 리스키 에셋의 excess return이 높을 때 expected excess return이 높으면 당연히 수익률이 높은 자산이니까 더 많이 디맨드 하겠죠. 더 많이 사고 싶어 하겠죠. 뿐만 아니라 theta가 높을 때 리스크가 높은 에셋일수록 덜 사고 싶은 거예요. Theta is low, meaning the demand for risky asset is going to be low. 하나가 더 있죠. When A is high, A가 뭐였죠? A is the risk aversion coefficient. When the risk aversion coefficient is high, in other words, when investor is more risk averse, then the demand for the risky asset is going to be low. Okay. Now, we can summarize some of the important features of the CARA-Normal case. First of all, because of the tractability, the model can be extended very easily to multiple assets. 자, 무슨 말이냐면요. 앞의 경우에 지금 우리가 어떤 베리어블들을 썼어요. 예를 들면 x 그리고 theta 이 두 개가 키 베리어블이었잖아요. 이 x랑 theta를 n dimensional 벡터로 extend를 할 수 있어요. In other words, we can extend this case to a more general n-dimensional vectors and the same mathematics hold. 따라서 이 앞에 example에는 리스키 에셋이 딱 하나였잖아요. 근데 그게 아니라 리스켓이 하나가 아니라 수십 개, 수백 대일 때도 똑같은 식의 수학이 적용되고 데리베이션을 할 수가 있어요. And the second important benefit of using the CARA-Normal utility function is that you can add background risk. 즉 무슨 말이냐? 지금 여기서 time 2의 asset이 이렇게 됐잖아요. current asset에 risk free asset만큼을 earn을 하는데 자 만약에 여러분이 theta amount를 risky asset 썼다 그러면 이게 next period wealth였잖아요. That was the next period wealth. But if you can receive some outside shock in the next period. And even when you have this outside shock in the next period, shock in terms of your income, 다음 피리어드에 인컴 샥이 온다 그러더라도 똑같은 식으로 계산이 됩니다. Except there's a hedging demand. If you want to see more details, see Campbell chapter 10.1.1. And also, and the third important characteristics and the benefit of the CARA-Normal case is that the equilibrium with heterogeneous agents is very easy to calculate because investor wealth, does not affect asset demand. What was the asset demand? That was theta. Okay. Also easy to calculate the volume of trade. Okay. And log normal returns can instead be used in this regard. 그런데 there are some downside of using CARA-Normal case. 자, CARA-Normal 케이스에서는 단점도 있어요. 첫 번째는 아까 말한 wealth irrelevance. In other words, whether you're Bill Gates or whether you're poor, doesn't matter how much you're. It's not going to matter for your risky asset demand. In other words, data was not the function of wealth. Was not the function of wealth. And that is not realistic. Okay? 왜냐하면 보통 웨alth 레벨이 높은 사람일수록 더 리스크 에셋을 더 많이 테이크할 수 있죠. 리스크 어버전이 낮아요. So constant risk aversion, constant absolute risk aversion is not realistic. The second drawback is that the utility function is bounded from above. The utility function was bounded from above, and wealth and consumption can go negative. Okay? Because there's no lower bound on asset returns. Why? asset return이 normal distribution을 따른다고 가정했잖아요. normal distribution의 특징이 뭐죠? Negative infinity is possible realization. In other words, wealth and consumption can go also negative because asset returns follow normal distribution. And the third downside is this case implies that the risk premium should grow because economic growth does not increase willingness to absorb risk in CARA case. 자, 이게 무슨 말이냐? 조금 이제 트리키한 케이스인데요. 이제 이코노미가 그로우하면 경제에 있는 웨alth 레벨이 증가하잖아요. 웨alth 레벨이 증가하면 investors risk appetite should increase as well. 그런데 카라 케이스에서는 risk aversion이 constant니까 absolutely constant니까 경제가 발전한다 그래도 에이전트들이 들고 싶어하는 리스키 에셋의 양은 한정이 돼 있어요. 즉 이 말은 뭐냐면 absolute risk aversion이 상존돼 있으니까 모델이 이제 스테이셔너리하게 핏되기 위해서는 리스크 프리미어가 증가하게 돼요. And the last bad property of the CARA-Normal case is that it's not easy to deal with multi-period returns because the product of normal random variable is not a normal random variable. 무슨 말이냐면요. 멀티피리어드 리턴을 계산하려면 투 피리어드 리턴을 이렇게 곱해줘야 되잖아요. For example, return from t to t plus 2 equals return from t to t plus 1 times return from t plus 1 to t plus 2. Okay. 이렇게 멀티 피리어드 리턴으로 가려면 리턴이 이제 accumulation이 돼야 돼요. 이렇게 곱해서 accumulation 돼야 되는데 the problem is that this product of the normal random variable is no longer a normal random variable. Okay, so it is not easy to deal with multi-period case with the CARA-Normal returns.